In order to be successful in your next calculus course, you have to be able to find an antiderivative, which is essentially the reverse of a derivative. In this course, we will look at some more basic antiderivatives, and in Calculus 2, you will look at more complicated antiderivatives and their applications. The process of finding an antiderivative is called integration. Let's look at some derivative formulas that we have seen up to this point in time. So here are some general formulas. We've taken derivatives of exponential and logarithmic functions, trig functions, and inverse trig functions up to this point in time. So it's important that you have these formulas memorized so that we can move in both directions, taking a derivative and finding an antiderivative. So please make sure that you have these formulas memorized. A function g is called an antiderivative of f if g prime of x is equal to f of x. To make a connection between a function and its antiderivative, we usually use the capital letter f instead of g. As an example, we would say that capital F of x is equal to x squared is an antiderivative of lowercase f of x is equal to 2x because the derivative with respect to x of x squared is equal to 2x. Example 1 says take the derivative of the following functions. So, in part A, we have capital F of x is equal to x to the 5th power plus 2x cubed. If I were to apply the first derivative, we would get that f prime of x is equal to 5x to the 4th power plus 6x squared. And that is that. So for part B, if we found g prime of x, we would get 5x to the 4th power plus 6x squared as well, because the derivative of a constant is equal to 0 if I were to apply the derivative to that. And on the other terms, we're just using the power rule. Okay, so for part C, capital H prime of x is equal to 5x to the 4th power plus 6x squared. Hopefully you're starting to see a pattern here. So in part D, capital T prime of x is equal to 5x to the 4th power plus 6x squared. I'd like to highlight, notice that here we could think about there being a constant of plus 0, minus 9, plus 7, minus e to the power of e. These are all giving the same derivative function. Now, what is the antiderivative of f of x equals 5x to the 4th plus 6x squared? This is where things change a little bit. If I wanted to denote the antiderivative, I would use the capital F of x notation, and my answer would be x to the 5th power plus 2x cubed. And now I need to include a constant because just like I highlighted above, all of those have constants. And I'm just going to do this using a capital C. And that capital C has a special name that we'll talk about in just a second. So, when we reverse the power rule, the general antiderivative of f of x equals x to the nth power is capital F of x is equal to x to the n plus 1 power divided by n plus 1 plus capital C. You can remember the reverse of the power rule as add 1 to the power and divide by that new power. Here's a theorem. If capital F is an antiderivative of lowercase f, then the most general antiderivative of lowercase f is capital F of x plus capital C, where C is some constant. We call C the constant of integration. Sometimes we may be given special conditions or initial conditions that can help us find the value of capital C. Otherwise, we just leave it as is to represent any constant value. Example 2 says find the most general antiderivative for each function. Part A says f of x is equal to negative 30x to the 5th plus 9x squared plus x. So in part A, I'd like to find capital F of x, and we're going to use the reverse of our power rule. So I'm going to take my term, negative 30x, I'm going to increase the power by 1, and then divide by that new power. I will do the same for the remaining terms, plus 9x, I will increase my power by 1 and then divide by that new power. And for my last term, x, I will increase the power to 2 and then divide by that new power. And we always want to make sure that we include our constant of integration. Now, I can go about and simplify this. So capital F of x is equal to negative 30 divided by 6. That will simplify to negative 5x to the power of 6 plus 3x cubed plus 1/2 x squared plus my capital C, and this is my final answer. Now, a way that we should be able to check our answer is if I take the derivative of this, it should return my original function if I were to use power rule. So let's do a quick check. If I multiply negative 5 times 6, that will be negative 30 x to the 5th power plus 9x squared plus 2 times 1/2 is 1, so that will be x. And then finally, the derivative of a constant is 0. So that does check out for us. All right, for part B, I'd like to find capital G of x, the antiderivative. However, it will be a little bit easier if we split this up into 3 individual terms. So actually, let me write lowercase g of x as negative 3x cubed times x to the 1/2 power. So I rewrote the square root. This is being divided by x cubed minus 2x over x cubed plus 2 over x cubed. And let's do a lot of simplification here. I can divide this x cubed, and that will leave us with negative 3x to the 1/2 power. And I can cancel out one of these x's, and then that would leave me with x squared in the denominator, but I'd like to use power rule or reverse power rule on that, so why don't I rewrite this as minus 2x to the negative 2 power, so I can bring that up to the numerator, and then my last term will be plus 2x to the power of negative 3, once again bringing that up to the numerator. Now that I have this simplified form of lowercase g, I can now use the reverse power rule. So capital G of x is equal to, I have negative 3x. I'm going to increase the power by 1. That gives me 3/2. And then I need to divide by that new power, 3/2. We'll go ahead and simplify this in a little bit. Minus 2x, I'm going to add 1 to the exponent. That makes us, or leaves us with negative 1. Then divided by negative 1 plus 2x, negative 3 plus 1 is negative 2, and divide by negative 2. Let's clean this up. So I have in my first term, we have division by a fraction, and so I can take the reciprocal, and I would have negative 3 times the reciprocal, which would be 2/3, and then that would simplify to be negative 2. So my first term is negative 2x to the 3/2 power plus 2x to the negative 1 power, and then minus x to the negative 2 power. I also want to make sure I include my constant of integration, so I'm going to put plus capital C, and here is our final answer. If you'd like to write those terms as fractions instead of having negative exponents, that's fine too. And if you did it that way, then we'd have negative 2x to the 3/2 plus 2 over x minus 1 over x squared plus c. That is also an acceptable answer for part B. All right, on to part C. And before I do that, I'm going to rewrite this thing here as minus x to the negative 1/2 power, so it'll be easier for us to use the reverse power rule on. I also need to take a moment and think about what function, when I take the derivative of it, gives me negative secant of x times tangent of x. So the antiderivative is capital H of x is equal to, and if you said negative secant of x, you'd be correct. Now I need to use the reverse power rule. So I have minus x. I'm going to add 1 to my exponent. That would make my new exponent 1/2, and then I need to divide by 1/2. And if we were to simplify this, I also need to make sure I include my constant of integration. I'm going to have negative secant of x minus, I can multiply by the reciprocal, so that's going to give me 2x to the 1/2 power plus my constant of integration. And remember, you can always write the square root of x instead of x to the 1/2 power as well. Example 3 says find h of x given that dh dx is equal to e to the power of x plus 20 times the quantity 1 plus x squared, and h of 0 is equal to -2. Before we do any kind of calculation, I just like to identify that this thing here, h of 0 is equal to -2. We talked about this earlier. This is called an initial condition. The reason that we're given an initial condition is so that we can solve for our constant of integration. Okay, now also I'm going to distribute this 20 in, and that will give us dh dx is equal to e to the power of x plus 20 plus 20x squared. Now, if I take the antiderivative of this, that will give me h of x, or just lowercase h, and the antiderivative of e to the x is e to the x plus the function that gives me a derivative of 20 is 20x. And then I'm using the reverse power rule. I have 20x cubed, and then I'm going to divide by that new power plus my constant of integration. Okay, so I said earlier we are given the initial condition so that we can find our constant of integration. Let's see how this works. I'm going to plug in 0. So I have h of 0 equals e to the power of 0 plus 20 times 0 plus 20 over 3 times 0 cubed plus c. And I know all of this together has to equal -2 based on my initial condition that we have here. This will become 0, this will become 0 as well, and then e to the power of 0 is equal to 1. So I have from this that 1 plus c is equal to -2, and if I solve for c, I get c is equal to -3. Now I can put all of this information together, and we get that h of x is equal to e to the power of x plus 20x plus 20 over 3x cubed, and we found that our constant of integration, c, is equal to -3, so I'm going to put -3 here at the end. Example 4 says find lowercase f of x given that f double prime of x is equal to sine of x, and we have two initial conditions here. F prime of 0 is equal to 1, and f of 0 is equal to 6. So I'm starting off with f double prime of x is equal to sine of x. And I'd like to go backwards and find f prime of x. So we must think about what function gives us a derivative of sine of x. And that function would be negative cosine, because if we took the derivative of that, we'd get back positive sine, and then I need to include my constant of integration. Now, before I take an antiderivative again, I'm going to use this first initial condition to help me find capital C. I know that f prime of 0 is equal to, I would plug in 0 for my x value inside of cosine. And according to my initial condition, this should all come out to be equal to 1. So I know that cosine of 0 is 1, and that would give me -1 plus capital C is equal to 1. And solving this linear equation for capital C, I would get that capital C is equal to 2. Now I can replace that in my formula that I have. So I would have f prime of x is equal to negative cosine of x plus 2. From here, I can take the antiderivative, and that would give me f of x is equal to the antiderivative of negative cosine would be negative sine of x, and then the antiderivative of 2 would be 2x. And now I'd like to use another constant of integration. Because we already used capital C here, I don't want there to be confusion, so I might use a different capital letter, capital D, to represent my new constant of integration. Another thing that you could do if you don't want to use that letter is here we could have called this C sub 1, and then we could call this C sub 2. That's an alternative way of naming these things. I'm just going to stick with capital D for now. And up here, I know that f of 0 is equal to 6. So I have negative sine of 0 plus 2 times 0 plus capital D is equal to 6. I'm going to use this implication arrow. This means implies that, or just implies. And sine of 0 is 0, 2 times 0 is 0, so the implication here is just that capital D is equal to 6. Putting this all together, remember our original goal was to find f of x, so lowercase f of x is equal to negative sine of x plus 2x plus 6. Example 5 says, suppose the velocity of a particle that is moving on a horizontal line can be modeled by the function v of t is equal to 3t squared plus 2t minus 8, where lowercase t is the time measured in seconds. Part A says, what function models the position of this particle with respect to time if after 1 second the particle has moved 6 meters away from its original position? We have this handy dandy table down here, and so we're given the velocity function, and we'd like to find the position function. And so in order to do that, going from velocity to position, we need to take an antiderivative. So let's start. We have v of t is equal to 3t squared plus 2t minus 8. If you are one of my students, you've probably heard this several times, but when you're using time as a variable, I highly recommend, even though when I'm writing normally outside of the context of mathematics, I write my t's like this, that can be very easily confused for a plus sign. So I very highly recommend that you add a little tail to your lowercase t. Now I'd like to find the position function, s sub t. I need to use the reverse power rule. I have 3t. I'm going to increase the power by 1, divide by that new power, plus 2t, increase the power by 1, divide by that new power, and then 8, I'm going to increase the power by 1, because you can actually kind of think of it as t to the 0 power. So I'm going to increase from t to the 0 to t to the 1, and I could also divide by that new power, and then plus my constant of integration. So let's do some simplification. We have t cubed plus t squared minus 8t plus my constant of integration. Now, something that we'd like to note, it says, after 1 second, the particle has moved 6 meters away from its original position. The reason that we're given this information is this is actually giving us an initial condition. And if you'd like, pause the video to see if you can figure out what the initial condition is. I will tell you, it tells us that s of 1, since our input variable is t for time in seconds, so s of 1 is equal to, it moved 6 meters away from its original position. So we're going to use this initial condition to help us find our constant of integration. Okay, so I'm going to plug in 1, and that will give me 1 cubed plus 1 squared minus 8 times 1 plus capital C, and I know that at the end of it, this needs to be equal to 6. If I do some simplification, I get 1 plus 1, that's 2. 2 minus 8 is negative 6, plus capital C is equal to 6, and that implies that capital C is equal to 12. So, coming back here, I'm just going to erase this and add 12 to this, and this now represents S of t. All right, so we finished up part A. Part B says, find the acceleration of this particle at time t equals 10. And again, as a reminder, we have this handy table. We're starting out with the velocity function, and it's asking us to find the acceleration. So if you look here using function notation, the acceleration is equal to the derivative of the velocity function. So to go from velocity to acceleration, we need to take a regular derivative. So we are in part B. I'd like to find the acceleration function, which we denote with lowercase a of t is equal to. Now I'm going to use the regular power rule. 3 times 2 is 6, t plus 2. And because I'm taking a regular derivative, we would not use a constant of integration. However, it does tell us not to find the acceleration in general, but specifically when t is equal to 10. So in other words, it's asking us to evaluate a of 10, where we're plugging in 10 for t. And this is equal to 62. And this is equal to 62. And I'd just like to write a sentence. The acceleration of the particle at t equals 10 seconds is 62. If we are thinking about the unit of measurement for acceleration, it's distance over time squared. And so in this case, we're being measured in meters, so 62 meters per second squared. Those would be the correct units for our answer in part B. Example 6 says, find the general antiderivative of the function lowercase g of x is equal to sine of 1/4 times x. We have capital G of x is equal to the function that gives us, when we take the derivative of it, gives us sine, would be negative cosine. And then we have our constant of integration. Now, this might be what a student would come up with, but if I were to take the derivative of this thing, the derivative of negative cosine would be positive sine. And then the derivative of capital C would be 0. And I would also need to use chain rule by multiplying by the derivative of the inner function, which would be 1/4. And if you notice, this is not the same function that we have right here. And so the thing that we came up with for capital G actually is not correct. The way around this is I'm going to have to throw in a -4 here, and that will get rid of the 1/4. So if I had a 4 right here, notice that this would multiply with the 1/4 and become 1 and would be good. So here is our general antiderivative for this lowercase g function here. Example 7 says, a ball is thrown upward with an initial velocity of 48 feet per second from the edge of a cliff that is 220 feet above the ground. Assume that air resistance can be ignored. Part A says find the ball's height above the ground t seconds later. Now, unless you've taken a physics class, you might not be familiar with acceleration due to gravity, and there are two values or constants we could use, depending on whether we're using the metric system or not. Because this example is using feet, we would not use the metric system value. So acceleration due to gravity is equal to 32.2 feet per second squared. Also, to make this example a little bit easier, I'm actually just going to round this and say that acceleration due to gravity is 32 feet per second squared. So for part A, I need to start with the acceleration function. A of t is equal to, the other thing is, because the ball is thrown upward with an initial velocity and then it starts to fall, and if we think about the traditional y and x axis, it will look something like that. Our acceleration needs to be negative because it's going to be falling downwards, so I'm going to make it negative 32. From here, I'd like to find the velocity function by taking the antiderivative. So v of t is equal to negative 32t plus capital C. We're also given this information. Initial velocity is 48 feet per second. And that is another way of saying v of 0 is equal to 48. So if I plug in 0 here, I have negative 32 times 0 plus c is equal to 48, which implies that this will become 0. So I am just left with capital C is equal to 48. So let's fill that in. My v of t is equal to negative 32 t plus 48. From here, I'd like to take the antiderivative again to get my position function. So s of t is equal to, I'm using the reverse power rule. I'm going to increase the power by 1, then divide by that new power. And we don't want to forget our constant of integration. I'm going to use capital D. Another thing we'd like to note is that there's 220 feet above the ground. That's where it's being thrown from initially, which means that our initial position or initial height is 220, which says s of 0 is equal to 220. This will help us to find our other constant of integration, capital D. Also, negative 32 divided by 2 is 16, or negative 16 rather. So I'm just going to rewrite that. Plugging in 0. So these will become 0, and we have that capital D is equal to 220. And putting this all together, we get that s of t is equal to negative 16t squared plus 48t plus 220. This is our final answer for part A. Part B says, when does the ball reach its maximum height? We already found the velocity function from the work that we did in part A. And if I were to graph the position function, if this axis was t and my vertical axis was s of t, I know that I have an initial value or height of 220, and it's going to be something like that, because we can see here that this is a quadratic function. And so it will have parabolic motion. And thinking about calculus, I'm trying to find essentially a local maximum. It's going to have a horizontal tangent line, which means that we can set the derivative, which in this case is our velocity function, equal to 0. And if I add 32t to both sides and then divide by 32, we end up getting t is equal to, this ends up being 1.5 seconds. And the question is asking when, so our final answer is after 1.5 seconds, the ball will reach its maximum height. And although it doesn't ask us, I'll just tell you, the maximum height that would be reached would be whatever s of 1.5 is, and I plugged it into my calculator. This number ends up being 256, and the units on this would be feet. So on my graphic here, this local maximum would happen after 1.5 seconds, and then this maximum height here would be 256 feet. Part C says when, so we're looking for a time since it asks when does the ball hit the ground? And this is actually not a calculus question because, again, this is a parabola and we are trying to find the time when the ball hits the ground, and when it hits the ground, it would have a height or a position of 0. So we can take our position function and set it equal to 0. So I have my position function. This is part C, negative 16t squared plus 48t plus 220 is equal to 0. Now, I can factor out a negative 4 from every term. That would leave me with 4t squared minus 12t minus 55 is equal to 0. And I can divide both sides by negative 4. And I can just use the quadratic formula on the thing that's inside the parentheses. And if you use the quadratic formula, you end up getting two solutions. T is equal to 5.5, and t is equal to negative 2.5. So we don't usually think of time as being negative, but visually we know that if I were to continue down here, this ordered pair here would have a t coordinate of negative 2.5, and then this one here would be 5.5. And so to answer our final question, this one is not in our domain because we're only thinking about positive t values or t equals 0. So we can say the ball hits the ground after 5.5 seconds. And that's it for part C. Example 8 says find the general antiderivative of the function h of x is equal to negative 20 over x squared plus 1. I'm going to start by rewriting h of x as negative 20 times the fraction 1 over x squared plus 1. I think that this will make it a little bit easier to see that capital H of x is equal to negative 20, and then the antiderivative of 1 over x squared plus 1 is arctangent or tangent inverse of x, and then we include our constant of integration. So that's it for this example and this video. Thanks for watching.